When it comes to talking about how much of your image is in focus, we have to discuss depth of field. Hey fellow photographers, what did you shoot today? We're going to be discussing depth of field, which is so important because it's one of the things that you can notice aesthetically about photographs right off the bat. You know, how much of the image is in focus? Is there selective focus? Are you blurring the background? And there's actually a lot of optics, math, and science that go behind what determines depth of field. And although it's not necessary to know all this information, if you understand the equations that we're going to go over, you're going to have a better understanding of what lenses are going to get what looks and what gear you need to get the photos that you want. So let's dive right in. We have our handy dandy sort of lens ray diagram, kind of like before. So let me explain what's going on. Here we have our lens, right? It has a diameter D, and this is going to be part of our sort of aperture opening, right? So the amount that this is open is going to be our diameter. And then we have these sort of three colored lines. Now this is not like the chromatic aberration video, I'm just color coordinating it so it's a little bit easier to understand. Let's start with this figure here, S. So this point out here is going to be our subject distance from the lens. As you can see, we trace these lines and it lands at a distance I, the image distance. This is our focal plane. Now we have points in front and in back of our subject, right? So one is deeper and one is closer, shallower, closer to us. So we have the distance of the near point, dn, and distance of the far object, df. Now when these rays converge, we're going to get things on the sort of depth of focus. We have depth of field out here and sort of depth of focus on the image plane. So we have the image that is projected by the near object is actually farther away, and the image of the far object is actually projected in front of the lens. Now from this ray diagram, we notice one thing, right? So the only point that's really in focus is our subject, if we focus correctly. So we have our focal point right there. Now the blue lines here actually extend past the focal plane, which means that they create some sort of blurry spot that is not focused to a single point. There is actually some measurable sort of, thickness to this spot that is on the sensor. We call this C. This is the circle of confusion surrounding this near point. Likewise, this far point actually converges in front of the sensor, but then the lines extend to that same other diameter, C, circle of confusion. So we have our object, near and far things that we're trying to focus, and so we're going to see how much of that we can get in focus at one time. So the amount in focus will determine our depth of field, how much we can see. So we have to make a lot of equations that will fully define sort of this system. So the first thing we can do is we can look at similar triangles. For example, if we look at this image near, right, this point way out here, this distance, which is going to be in minus I, right, because it's in minus the image distance, so it's just that height of this triangle to this bigger triangle, which is this entire distance is in, the relationship of those two is going to be equivalent to two other sides of the triangle. So let's take the base. So we have this small height is to this big height as this small base, C, which we've defined as circle of confusion, is to this bigger base, which is D, the diameter of our lens. Now we can do a similar thing for the far image. If we have I minus IF over IF is also equal to C over D, we're going to bring back our F number equation from previous video, where N is equal to F over D, focal length over diameter of the opening. And we have to bring in our thin lens equation way back from the lens videos. So we have 1 over F is equal to 1 over distance to the object plus 1 over distance of the image. So here we've defined that as, in this case, 1 over S plus 1 over I. And we can also make another set that is equal because we have other triangles, other focal points. So we can also have 1 over F is equal to 1 over the distance of the near object plus 1 over the image of the near object, and 1 over F is equal to 1 over the distance of the far object plus 1 over the image of the far object. So now we have a system of 6 different equations, and we can sort of do a lot of algebraic manipulation to arrive at formulas that define what exactly is this near distance and what exactly is this far distance. Okay, so I've saved you a lot of trouble and a lot of algebra and just written the results from those system of equations that we solved, and this is what we get. So we get that the distance of the near point is defined by s times f squared over f squared plus n times c times the quantity s minus f. And it's likewise for the far object, except that this is a minus sign in the denominator. So the difference between these 2 points, the near and the far point, this is going to determine how much of our image is in focus. And you don't have to do these calculations, but you should understand what each of these things is telling you and what factors go into determining what the depth of field is. So let's take it one step at a time. Now, I said that a smaller aperture is going to give you a larger depth of field. So remember that a smaller aperture is a higher F number. F number is n. So let's see if that holds true. If we increase n, we increase a number in the denominator here, that's going to make this entire fraction on the bottom, the denominator, bigger, which makes the whole fraction smaller. So dn will decrease with the higher f number, which means that this point will actually be closer in towards the lens. Now, the opposite is true for df. So a higher f number, smaller aperture, so we have like something like f22 in here, right? Very large. Makes this smaller because it's going to be, some number, some positive number minus something. So this becomes smaller. Something smaller in the denominator makes the entire fraction larger. So df actually gets extended. So the higher the f number, n in this case, the smaller the aperture, right? So if we're going from a wide aperture like 1.4, we're going to get a shallow depth of field. But if we go to f8, f16, this is going to start expanding, and we're going to get more and more of the picture in focus. That's why people use high f numbers in order to get more of the picture in focus. If you want a shallow depth of field, you're going to open up the lens, right? Which means making a larger aperture a smaller f number. So if you want some subject isolation, you're going to be shooting down at f2.8, f2, 1.4, something like that. And that's going to shrink the depth of field. It's going to shrink the amount of the image that's in focus. Now, when I discuss these different factors like n and s and f, we're holding everything else constant. So if I change, multiples of these things, if I change the f number and the focal length and my subject distance, then it's less clear what happens. But if we take them one at a time, we're going to understand the relationships. So that was f number. Now, forgetting f number, and let's look at subject distance. Subject distance is a really important one. So when subject distance increases, the further away the thing you are that you're focusing on, the more depth of field it has. Now, it's not really intuitive right away, so let's understand why. Well, we have s in both the numerator and the denominator, so you'd think they kind of cancel out. But this s is going to be multiplied by this factor here, and this is usually less than 1. So this is some number, and this is some decimal usually, depending on the circle of confusion of your film format. So what happens is that, yes, the distance of the near object increases with an increase in subject distance, right? So imagine this whole thing, as we increase subject distance, it's moving outwards. So this increases and this increases, but the key here is that this, df, the distance to the far object, increases at a faster rate than does the distance of the near object. So imagine as you start focusing further and further away, right, it's like a race. The far point is moving quickly, and this near point is not moving as quickly. So you're going to get something like this, where, yes, both points are getting further and further away, but because this point is getting further faster than this point, this is expanding as you focus outwards. So it's a little hard to see, but the further away your subject is, the more depth of field you have. So if you pose somebody and you get in close, right, the closer you are, the shallower the depth of field. So if you're doing an intimate portrait and you're getting someone's headshot and you're in really close with a lens, right, you're going to get that shallow depth of field. But if you tell them to back up, and you're going to get head and shoulders or even full body, you're going to have a shallower depth of field if you keep everything the same. If you keep the focal length the same, if you keep the aperture that you're using the same. Again, without changing anything else, subject distance, only changing subject distance is going to increase the depth of field the further away you get, the longer the camera to subject distance. Changing C is a little difficult to understand, and I'm going to probably just save that for an entire other video because there's so many factors that go into what makes a circle of confusion. And honestly, it depends on what you make the print size, how far you're viewing the print. There's a lot more factors that go into C, but usually for if you're using a full frame camera, it's going to be the same, right? Because as long as you're making, looking at things on a similar computer monitor or similar print size from a similar viewing distance, we can keep that constant from camera to camera. Now, when we switch formats and we go from camera to camera, there's a lot of controversy about what happens in depth of field and that kind of thing. That is a whole nother video. So for right now, we're just going to take C as given for a given film format, full frame, micro four thirds, crop, doesn't matter. So the last thing we need to talk about is F, focal length. So this is another one that is actually quite controversial, and people don't think that depth of field changes with the focal length of the lens. And because what they're doing is they're playing with the notion of creating the same image, right? So if you change focal length, if I go from a wide angle lens to take a portrait, and then I go to a telephoto lens to take a portrait, I would have to back up with the telephoto lens to get the same angle of view, the same sort of size of my subject. So if I'm photographing a person with a wide angle lens, I can get pretty close to them, right? I can get really close, and that wide angle lens is going to take a nice head to toe shot of that person. But if I'm going to a telephoto lens, I'm gonna have to back way up in the studio and then take that shot. And it's that movement, remember we just talked about the subject distance changing. It's that movement that changes the depth of field, not the focal length. Now remember, if we're holding everything else constant and we're just looking at focal length, wide angle lenses tend to capture a larger depth of field. Why is that? Well, we can just look at the math. So you notice that this right here, this positive times a negative makes a negative, right? So if we have we have this number over this number minus some factor that's based on focal length, this becomes smaller, which makes that this is bigger. So that means that distance of near gets bigger. Then what we have is as focal length increases down here, a negative times a negative is a positive, which makes this thing larger, which makes this entire fraction smaller. So as focal length increases, as focal length gets bigger, this number is going to get bigger, and this number is going to get smaller. So as focal length increases, dn, the near object, gets closer to the subject distance, and df gets shorter. It gets pinched. So this goes inwards like this, the longer the focal length of the lens. So if I'm using like a 200 millimeter lens, I'm going to get a shallow depth of field way out here, right? And if I'm using a wide angle lens, the opposite happens, right? So if we lower f, the opposite of what I just said happens. So we're going to get a wider depth of field when it comes to wide angle lenses. Now there's this other misconception that keeps floating around that says that, oh, you just have to worry about, just set your focal point, and then you know that 1/3 in front of the image and 2/3 behind the image is going to be in focus. Well, that's not really true at all. It will work at certain focal lengths and apertures and subject distances, and as you get further and further out, what is behind, this area behind actually encompasses a larger percent of what is in focus, right? Because that makes sense. And the reason that makes sense is because think about our subject distance. So the further and further we go out, the more and more is in focus. So that means that, the more and more it's in focus on the tail end versus this end. But let's do one numerical example to explain why this is a common misconception and it doesn't really hold any water whatsoever. And you should really think about what is happening in regards to these numbers and what is contributing to your depth of field, and not just go by some silly rule of thumb. Okay, so I've written a numerical example here, and let's solve this using these equations and see what this means for our photographs. So I'm taking that nifty 50, the nifty 50 lens that is in a lot of people's kits. So we're at 50 millimeters focal length. We're going to be shooting wide open because we want that shallow depth of field at f1.8. Remember that n is our f number, so we have 1.8. The circle of confusion in this case is 0.029, and this is off a table for full frame cameras. This is the accepted circle of confusion for different metrics. You can look these things up online or on Wikipedia. And our subject distance, we have to have the same units as here, so we're going to say 1,000 millimeters, which is 1 meter away, so about 3 feet away. So we're taking a nice close portrait of that person. Let's see how much depth of field we're going to get. So I'm going to use my notes and cheat, but if we plug these numbers in, we find that the distance of the near point of focus is 980 millimeters, roughly, give or take. Distance of the far object is roughly 1,020 millimeters, give or take, some rounding. So the difference is about 40 millimeters, or about 4 centimeters, so not even 2 inches. So we're talking about a very minuscule depth of field. Now this is important to note because think about what you're trying to get in focus with a portrait. So we have about 2 inches, right? So 2 inches is going to, if my eyes are in focus, if I have an inch in front, an inch in back, and you notice that here, the near point, it's pretty much 50-50, right? So 50%, so it's 40 millimeters difference, and our subject distance is 1,000, right? So there's 20 millimeters in front of the focal point and 20 millimeters behind. So this is actually 50-50, which debunks that whole 1/3, 2/3 rule. So we have about an inch in front and an inch in back of the focal point. Well, an inch in front, I don't know, maybe my nose is a little bit bigger than an inch long. So basically the tip of my nose will be not as in focus, which might look kind of weird if you're looking at my eyes in a portrait or someone else's eyes, and the tip of their nose is a little fuzzier than what's in sharp focus. And then your ears aren't going to be in focus for sure, because that's more than an inch behind where your eye is. So maybe this isn't the best choice, right? Because maybe we get some sort of distorted reality, and when we see things that we don't necessarily see in nature, our brain gets a little bit confused, right? So if we're trying to, shoot wide open, f1.8, it's going to give you this nice blurred background, which is totally true. But in this case, when we're this close to our subject, we're actually getting such a shallow depth of field that it may not look natural. It may not look natural to have everything from here back of the person's face blurry, or have the tip of their nose blurry in front of the focal plane. So here we can do a few things, right? We can stop down. If we really like the framing, the composition that our subject distance is at, we don't want to move forward or backward, right? We like where the composition is at. We can stop down to get more depth of field. So we're going to increase the aperture, the F number, by decreasing the size of the aperture, and we're going to get more in focus, right? And maybe we want the whole face in focus, right? So we have to look at what that is. Then the other thing we can do is, let's say we don't want to use we're okay with changing the composition, right? We can actually move further away, increase or push our subject back, increase the subject distance, and by increasing the subject distance, again, we're going to get more depth of field. So we can still shoot wide open, but if we push the subject back a little further, we're going to get more of their face in focus. So there are all kinds of things we can do. Another thing would be able to change the lens, but if we were using that lens, the only lens we have, we got to work with the other variables. So you can see by changing these different variables, we're able to get different results. We're able to get the look we want, and we're able to get something that's more or less realistic. Now, people love those portraits where the background is completely blurred out, which is fine, and we can help that by having our subject far away from a background and using a wide open aperture, a small f number. But we also have to make sure that that picture looks realistic. And I don't know, I'm having a hard time thinking that 4 centimeters, not even 2 inches, is going to look realistic when we're that close to our subject. Just focus on the eyes. Whatever you're doing, whether it's portraits, right? You should look at a portrait lens, which are usually in somewhere between the 50 to 85 to even 135 millimeter range. Whether you're doing, head 3/4 length, head and shoulders, or a tight portrait, you should look at that lens, what it says about that lens, what these equations say about that focal length, what subject distance you need to get some sort of acceptable depth of field, and what aperture you should be shooting at. So you have to take all this into account. On the other end, if you want like a landscape lens, well, it kind of works out that wide angle lenses produce great depth of field, or larger depth of field than a telephoto lens, because you usually want all of your subject in focus. But there's also different things about where do I set the focus point. Do I set the focal point or the subject distance to infinity and focus that way? Is that going to be the greatest depth of field? Not really. There's actually a distance called the hyperfocal distance, which applies to a lens and certain apertures, which is going to give you the maximum amount of that photo in focus. So we're actually going to talk about that in another video. So these things, these considerations, using simple math and these diagrams, which hopefully are a little bit intuitive now that I've explained them, can give you a really good idea of what tools you need to get the photos you want and sort of what techniques we can use to get the look we want with the gear that we have. So remember, when we're talking about aperture, we're talking about the amount of light that's entering the lens by making the aperture opening bigger or smaller. So we're controlling the amount of light that enters the lens for exposure purposes and has the added consequence or benefit of controlling how much of our image is in focus. That's why aperture is one of the most important things when it comes to the aesthetic look of our photographs. We also have two more things on the exposure triangle to talk about. Eventually, we're going to talk about shutter speed, which can also produce an aesthetic quality to our images. So all of these things both control the exposure and the look of our photographs, which is why it's so important to understand them. So go out, try shooting things at different apertures, see how you like the results. Maybe, there's depth of field calculators online. I'll probably link a few, and you can just plug this stuff in so you don't have to do the math. And you can kind of look at different focal lengths and different subject distances, what is going to happen to the depth of field, and is that something that I want in my photographs? So go out there, try using different aperture settings, different lenses, different subject distances, and see that effect on the photo, how much of it is in focus. So go out there, and until next time, as always, happy shooting.